So something really cool with bones is they are able to remodel. So they grow and shrink based on the amount of use. So the more that you use them, the greater the density is and the greater the size of the tuberosities are. Tuberosities are little sites of muscle attachment. So the more your muscles are pulling on the bone, the bigger those tuberosities get. Bone density is a good thing. It prevents fractures and decreases the risk for osteoporosis. As we age, our bone density decreases and our collagen quality decreases. So this puts us at risk for bone fractures and disease as we age. Remodeling is also really useful to gain access to calcium. So if we have excess calcium in the blood, we deposit it into the bone, and if we have too little calcium in the blood, we take it out of the bone. So we maintain calcium homeostasis through this process of remodeling. So two different types of growth. There's interstitial growth, which is the lengthwise growth that you see in kids. Apositional growth is the widthwise growth, and this is happening just on the outside, and this is the growth that you can have throughout your whole life. So interstitial growth is the part that's happening in the epiphyseal plates. There are 5 different zones in the metaphysis in the epiphyseal plate. So the first zone is here. This is what we call the zone of resting cartilage. So at this point, the cartilage cells here aren't really doing a whole lot. The use of this zone is to bind the epiphysis, the end of the bone, to the epiphyseal plate. In zone 2, the chondrocytes are actively replicating. So you can see each of these little purple lines is a chondrocyte, and they kind of stack on top of each other as like little quarters. Next is the zone of hypertrophic cartilage. If you remember, hypertrophy is increase in cell size. So the cells replicate in zone 2, and then in zone 3, they increase in size. The combination of these two is what gives bone their length. And then in zone 4, the minerals get deposited, and this traps the chondrocytes. They don't get any access to nutrients, so they actually die here. And then this allows the blood vessels to come in, and they bring bone cells with them. Apositional growth is the only type of growth that you can have as an adult in your bones. So this is increasing the width of the bone. So this is a bone of an infant, and you can see it's growing in width until adulthood. So the outside gets deposited, and we keep increasing the width by depositing on the outside, and then the osteoclasts on the inside are actually making the medullary cavity larger. So you're adding to the outside and dissolving the inside. So hormones, there are a bunch of different hormones that you need to know for the bone section. The first few on the slide, so growth hormone, cleverly named, stimulates growth of cartilage in the epiphyseal plate. So during puberty, a bunch of this growth hormone gets released, and that's what triggers the growth spurts. Thyroid hormone stimulates the metabolism of the bone cells. Sex hormones like estrogen and testosterone accelerate bone growth. So towards the end of puberty, you'll end up with higher levels of these sex hormones. And that means that the end of growth is coming soon. Glucocorticoids are responsible for regulating blood glucose, but in bone, if there are high levels of them, you can have increased bone loss and impaired growth. So glucocorticoids are released in terms of stress. So individuals that are young and have a high amount of stress long term can actually have growth stunted. Serotonin, you guys may have heard of in a different context, but serotonin is regulating the rate of bone remodeling. The last three I'll go through in a little bit. So I've talked about how important calcium homeostasis is and how the bones act as a reservoir for calcium in case the body needs it. So calcium in the body is really important in muscle contraction and in nervous system communication. Heart beating is part of muscle contraction, and blood clotting is also really important with calcium. It gets regulated by these two hormones, calcitriol and parathyroid hormone. So one way that calcitriol regulates blood calcium is through the skin, which we briefly talked about last unit. So UV light, in terms of sun rays, comes in, hits the skin, converts vitamin D3 into calcidiol. Parathyroid hormone gets secreted by the parathyroid gland, and it tells calcidiol to transfer into calcitriol. Calcitriol is the one that we really care about. Oops, and I deleted it. Calcitriol is active vitamin D, and it works on the gut, so it works in the intestines to tell your body to absorb as much calcium as possible. So when you consume, a glass of milk, the calcium is being absorbed into your blood. So parathyroid hormone and calcitriol both get secreted when calcium is low, and the goal is to increase blood calcium. So we do this in kind of three different ways. We increase osteoclast activity, so we're dissolving bone and releasing the calcium. We also increase kidney reabsorption of calcium. You guys will go through the kidneys in Bio 202, but basically there's a bunch of tubes, and depending on what the body needs, certain things like calcium can be reabsorbed or they can be peed out. So parathyroid hormone tells the kidneys to reabsorb the calcium back into the blood. Calcitriol, like I just said, increases absorption of calcium in the GI tract, gastrointestinal tract. So calcitonin is the opposite. It is secreted when blood calcium is high. So we need to decrease our blood calcium. So we do this by inhibiting osteoclasts. If you inhibit osteoclasts, there won't be any more dissolving of bone, so you won't get calcium into the blood. The other way is increasing kidney loss of calcium. So instead of reabsorbing the calcium in the urine, it just gets peed out. So calcitonin is really important in kids. They are remodeling their bones at a very quick rate. As kids are growing, their bones are lengthening. There's a lot of osteoclast activity. In adults, there's not a whole lot of bone remodeling happening, so we're not losing a whole bunch of calcium. Here, this is kind of just a map of what goes on. So here it says low blood calcium. The receptors are on the parathyroid glands. They get information, hey, there's low blood calcium. So parathyroid hormone is released, and the calcitriol is also being converted. The two of these work together on the bone to increase activity of osteoclasts, increase reabsorption of calcium in the kidneys, and increase absorption of calcium in the intestines. All of these together lead to blood calcium levels being back to normal. Hypocalcemia is the deficiency of blood calcium. So hypo is too low, cals is calcium, and emia means in the blood. So low calcium in the blood. This results in excessive excitability of nerves and muscle tissues, excess spasms, tremors, Individuals are not able to relax that are hypokalemic, and they cannot breathe, and they die by suffocation. Hypercalcemia is excess blood calcium. This results in the opposite, so very unable to be excited, very tired, weak. Your heart quits beating because it needs calcium in order to have contraction. Hypercalcemia is very rare. Why do you think that is? And that's because excess blood calcium just gets put into the bone. If there's too much calcium, it just precipitates into the bone. If there's too little, it's a little bit harder to get calcium that we need. It takes longer for the osteoclast to start working. There's only so much bone we can dissolve. Okay. I will pick up with healing fractures on the next video.